down here, what particle is this? What exchange particle is the squiggly line? It's going to be a photon. What about this one over here where there's a dotted line? That's your weak force, or your EMF. There's another one too, which is going to be the strong nuclear force. That one looks a little bit like this. So these are the different ways that we can see particles moving across, or at least bosons moving across. Let's do another example. Proton turns into my neutron, and my beta particle, and my neutrino. Now, why doesn't the neutrino, first off, have a line over it telling us that it's an anti-neutrino? The neutrino that comes off of it has to have the opposite lepton charge as the lepton that's given off. So in this case, this is an electron that is not negative, it's an electron that's positive. So it's called a positron. So it actually comes off as a positive electron, which is the electron's antiparticle, called a positron. The electron's antiparticle then, because it's an antiparticle, has a paired lepton with it, which is not an antiparticle. It's a neutrino. So we always have a non-antiparticle with an antiparticle together. And so first thing we want to do is just draw our diagram. Space into time. So in this case we've got proton coming in, and at some point in time proton turns into a neutron. So down here I'm going to call this a proton. Down here I'm going to call this a neutron. And then we can put an arrow showing that this continues off in that direction. And from that vertex then, it's going to give off an exchange particle. And that exchange particle, we're going to make it a dotted line this time. The dotted line then is going to come to another vertex. And at that vertex, it's going to split into two other particles that will go off in different directions. You guys know that those particles are going to be the positive electron, or in this case our positive beta particle, and also my neutrino. And my neutrino then, a regular neutrino with my antiparticle, they pair up nicely. Once again, we're going to take our conservation of charges and go through right from the very beginning to the very end. Let's start with our overall charge. The charge of our proton is 1. Charge of our neutron is 0. So there's a boson in here that has a charge to it. And what we're trying to do is to figure out what is the charge of that boson. And that gauge boson, it's either W plus, W minus, or a Z boson. And in this case, all of these are going to be charged examples. What's the charge of that boson? If we have 1 coming in, 0 coming out, well, we know it has to be a plus. That's right. It's our W plus boson. And so our charges are conserved now as our charges go off this direction. Let's now talk about our number of baryons. How many baryons do we have here? Well, we have one baryon. Here we have one baryon, which means at the vertex we have one coming in, we have one going out, which means there shouldn't be any baryons going that way, to the right. The next step then is to look at our lepton numbers. And our leptons are our electrons, our mu, and our tau, along with all their antiparticles. So proton does not fall into that category. Neutron does not fall into that category. My boson does not fall into that category. But these, in fact, do. So my lepton then, in this case, is, because it's an antiparticle, it gets an anti-lepton number. So it becomes -1. So the lepton number for this positron is a -1. My lepton number for this neutrino, because it's simply a neutrino, is 1. Together they make up 0, and our number is conserved. Now, just like these over here, I could say that Q here is going to be 0, and my Q is going to be 0. And my baryon number, Q0, will also be 0. So basically it's looking at all of the conservation of all the different types of charges for it. And really it's a way to keep track of them. What do you think?
I didn't know the B number.
Baryon number. Figure out what baryons are.
What is matter made of?
Baryons are all the things that are made of quarks. So going back to the elemental particles video, and these hadrons and leptons are made of different things, and that's part of how we classify them. The hadrons themselves are broken up into 2 other categories, baryons and mesons. And baryons might be familiar to you. Baryons are the ones that we know of as neutrons and protons. Baryons are made of 3 quarks, and mesons are made of 1 quark and 1 antiquark. Anything that's made up of quarks, including protons, neutrons, and also those mesons. So we've got protons and neutrons come in triplets of quarks, and we've got mesons that come in pairs of quarks. And I told you guys the one about the ducks that quark and the ducks that quack. Just checking. And really, it just takes practice. After you play around with it a little bit, it gets to be a little bit fun. If you remember from the nuclear binding video, what I did is I drew in some of those exchange particles between protons and neutrons in the nucleus. And those were gluons. And those gluons are from the strong force. And so we've got photons. We've got our electroweak force. And we've got the strong force, which are those gluons. And those gluons are the ones that hold the nucleus together. So if I was drawing those particles, those dots in the middle of that video, I think I put two spheres together and I was drawing dots in the middle of the 2 spheres. That was the strong force. If we were going to depict that in a Feynman diagram, they would be loops like this. So pretty cool.